All right, folks. Today we are going to be learning our next subunit, which has to do with the binary number system. And I touched base briefly on this throughout the past couple of lectures about the importance of binary, and we're going to kind of get into this with a little bit more detail, but we're not going to get too complex with this. So as we stated earlier, the binary numbers are sequences of zeros and ones. All right, and we use binary, I say the computers and our devices use binary to compute any sort of data that streams through it. As you can see, the bullets over here, numbers, text, letters, images, videos, anything that your computer uses and operates on daily is all done through binary. So we're very familiar with the decimal system, and that's what we use in order to make sense of numbers and things around us, where the computer uses binary. There are other forms of systems out there. There is an octal system, which is using numbers 0 through 7. There's a quinary system, which uses 5 numbers, basically 0 through 4. There's a hexadecimal system, which is 16 characters and uses numbers 0 through 9. And then because there are no other numbers, once you get past 9, it goes into letters, A, B, C, D, and so on and so forth. All right, so those are the number systems that are used frequently within computational processes. So let's look at some similarities between binary and the decimal system. So as you see here, we have the number 542, and 542 is the number in question. And how would we break that down if we were to teach this to somebody? Well, we look at it from a position standpoint, because regardless of what number system you use, it's called positional number systems. So if I look at the number 542, all right, back in our old school days when we were in elementary school, we first learned that, all right, this first number here, this is your first column, all right, this is your ones column, and then the next column over, that is the tens column, and then the next column over is the 100s column, and so on and so forth. And it's positional based on that moving forward. All right, and so what we can say is we can break down the number 542 as 500, as 40, and then as the number 2. All right, and then we add them all together, and then we get that number 542. All right, so just like with the decimal system, we can also apply the same concept when it comes to binary. It's a little bit different, and it's a little bit of a mindset shift, but we can definitely do it. So within our decimal system, though, we have 10 numbers, and again, we have 0 through 9. All right, and then after 0 through 9, well, what happens? Well, if I kind of use that number 542 above as an example, I can start counting, and I can go 1, and then the next the next number is obviously 2, and that will continue down until we get to 9. Well, then what happens with 9? Well, we have no other numbers to really work with and use, so what I need to do is I need to take that number 9, and when I add 1 to it, I'm reverting back to the beginning, all right, which was the number 0, and so I'm going to replace 9 with a 0. But what I'm going to do now is I'm going to shift over from my ones column to my tens column, and we're going to start this whole process all over again, and we're going to place a 1 there. And then the 0 becomes a 1, and then the 1 becomes a 2, and then the 2 becomes a 3, and so on and so forth, until we obviously get to the number 19, and the 9 will then revert to a 0. The 1 will then count upward to the next digit, which would be a 2. And so the numbers change based off of that system. It's always the rightmost digit is always counting up by 1, and when it reaches its maximum number that it can possibly do, it recycles or reverts back to its starting point, which is 0, and then the next digit over will flip up by a count of 1. And then obviously that keeps going until we get to the number 99. And then when we add 1 to the 9, all right, the 9 here will revert to a 0, which causes the 9 on the left in the tens column to then count up by 1. But when that counts up by 1, all right, it has to then flip and revert back to its original, which is 0. And then since there's no space in the next column to the left, which is the hundreds place, we then add a 1 there because that would be the next digit when we count up. Because if you want to think of it, before we put the 1 there really technically is a 0 there, but we don't write obviously the number 099. We just leave it as 99 and disregard the 0. But if we wrote it in there as 099, we'd see that when the the rightmost 9 counts up to 1, it reverts back to a 0, causes the leftmost 9 to then add 1 to it, which then reverts that back to a 0, which then causes the 0 to count upwards by 1, and therefore that would then turn into the value 100. Now obviously when we look at numbers, we don't think of it from this perspective, but the reality is that's what's happening when we look at a positional number system, because that's exactly how the numbers shift and change. So with that in mind, we're going to think of that when it comes to the binary system, and we're going to add the same way. All right, so now looking at the binary system. So again, remember that the binary is used specifically in computers for a very specific reason, because when it comes to the binary system, that's how the computer understands data that needs to be processed. All right, the 0 means no electricity running through the gate or through the circuit, and the 1 means that there is registered electricity running through the gate or the circuit. All right, so now we have the 101. Oops, there we go. So we're going to use 101 from a binary perspective. Now, again, because of binary, then obviously the prefix bi meaning 2, the binary system uses 2 digits. Unlike the decimal system, deci being 10, using 10 digits, the binary system uses 2, and the only 2 digits that a binary system can use is a 0 or a 1. So meaning that it cannot go past the number 1. So when we look at an example, as in the number 1 for a decimal system, well, actually, let me look at the 0 for a decimal system, and then we'll put binary over here. Well, 0 is just 0, and since we can represent that same number in binary, we'd also use a 0. And then in a decimal system, when we use a 1, well, in binary, we can also represent 1 as 1, so we can just place a 1 there. But now what happens in a decimal system, when we get to the number 2, all right, we cannot represent that number 2 in binary because we can only represent 0 or 1. So if I were to look at a binary number, and let me just write 3 zeros here for now, this would be representation of 0 as well. If I were to change this rightmost 0 and put a 1 there, all right, this would also represent 1. But now because of the fact that I cannot put a number 2 in place of that 1, what has to happen is that just like in the decimal system, when we reach the number 9, it resets itself back to 0. Well, this 1 is going to reset itself back to 0, which is going to cause this next most digit to have to increase by 1. And so we'd put a 1 there. And then we have obviously that leftmost 0. So even though this kind of looks like the number 10, it's not. It's technically the number 2. Because this rightmost digit over here has a maximum value of 1. Okay? And then this middle digit here, all right, has basically its place value is 2. The next digit over would have a place value of 4. The next digit place value would be 8. After that would be 16, and so on and so forth. All right, so just like in a binary system where everything, they call it, just like in a decimal system, they refer to it as base 10. So that means that you can pretty much figure everything out based off of a power of 10. Well, in a binary system, everything is base 2, meaning that whatever number that you're dealing with, it's always a square, or it's always a base 2 of that factor. So therefore, when we look at a binary set of string of numbers, draw eight zeros here. Okay, the place value that this ones column has is 1, but then we would square that, or it's a multiplicative of 2, so it's 2 in the next column. Okay, it's a multiplicative of 2 to the next column, so that would be 4. Multiply the next one by 2, which would be 8, by 2 would be 16, would be 32, would be 64, and it would just continue on by a multiplication of 2 from there. All right, so that means if I needed to represent the 101 as binary and convert that into a decimal number, I can easily do that. So let's check out, first let me erase this over here, and we can move on and we can actually check out some examples and hopefully make sense of this a lot more. All right. All right, so what we are going to do is we're going to look at an example and we're going to convert the binary number 10101 into a decimal number. Now, the importance behind this is that, for us to understand what's going on, this is how we need to understand how computers operate. Because like I said, a computer will operate this value, 10101, and it will understand exactly what this means based on what it's trying to accomplish or calculate. But for us, we need to do a little bit more processing to kind of understand, what the computer is thinking when it's using this string of numbers. So like I mentioned before, we're going to draw the binary number as is, 10101, all right? And then right above it, what we're going to do is we're going to write out what does each column represent. So remember, everything is a factor of 2. So the first column is always going to be 1. The next column over that is going to be 2 times 1, so it's going to be worth 2. The next column over will be 2 times 2, which will be 4. The next column over will be 2 times 4, which is 8. And then the next column will be 2 times 8, which is 16. And so when we look at 10101, all we have to do is say, okay, whenever there is a place of a 1, okay, here, here, and here, what we're going to do is we're going to add that maximum value that that column can hold. So because this first column is on, all right, we're going to assign the value of 1 to that column. Because the next column over is off, it's a 0, we basically disregard that and we're just going to add a 0 there. We go to the next column, it's on, all right, so therefore the maximum value that column can have is 4. So we're going to have to add a 4 to that. We go over to the fourth column, okay, the value is 0, and so because that's off, we're just going to add 0. And the next column, the last column, the fifth column, is 1, so therefore the maximum value that column can hold is 16. And so what we see, as you can kind of see down here, they did as well, but I did it out a little bit more by adding those zeros in there so you can specifically see which column value is being added and which one we're kind of disregarding. And so we have a 16 plus a 4 plus a 1, which gives us the value of 21. And then that is the result for the binary number that we have. All right, so let me do another, because I think my slides here don't have any additional examples. So let me just kind of up top here, let me write a number out. So we'll use 1001101. All right. So again, remember the first thing that we're going to do is we're going to look at each column. We're going to assign a value. So the first column that I have, I'm going to draw a line, and I'll use a different color for this. So the first column has a maximum value of 1. Second column, maximum value of 2. Next one, maximum value of 4. Next one, we have 8, 16, 32, and then 64. All right, and so when we look at the numbers that we have, okay, so column 1 here is on, so that means we're going to add the value 1. The next column over here, all right, is off, it's 0, so we're going to keep it as 0. The next column is on, so it has a maximum value of 4, so we're going to add 4 to that. The next value is on, so therefore the maximum value that column can have is 8. The next two columns, all right, are off, so they're both zeros. So we're going to have to add zeros for both of those columns. And then the last column over here is on, so therefore its maximum value is 64. So we're going to have to add 64 to that. All right, and then in the end, all we have to do is we just have to add everything together. So 64 and 8 should give us 72. 72 and 4 should give us 76. Plus 1 should give us 77. And then that should be our final answer for the binary code 1001101. All right, that should be equivalent to the decimal of 77. All right, so let me get rid of this, and then we'll continue on. Because the next step, what we're going to look at is basically doing the exact opposite, but rather than converting binary into a decimal, we're going to convert in the opposite direction and do decimal into binary. All right, so we do the same thing. All right, we have the number, let's just say, okay, they're giving us over here the number 25. So we want to convert this number 25 into a binary number. So we're going to do the same thing like we did in the last format, all right? We're going to, but this time, rather than obviously having the binary numbers to start, we're going to write out all zeros initially, all right? And then above it, what we're going to do is we are going to write out, again, the place values that each column has. So if the number is 25, obviously we're not going to stop at 16. You're always going to want to go to the number that is greater or higher than the value you're trying to find. So for example, if the number was 34, I needed to find, you wouldn't use 32, you would add one additional zero, and then that would be 64, because you always want to have that one space beyond the number. So again, if the number is smaller, like in this case 25 is greater than 16, we wanted to always go to the next column over and make sure that we have another spot or space available. All right, so with that being said, let me erase this and we'll continue on with the notes, and then we'll finish up the problem and solve it. And are they using the same? Yeah, they're using the same number here. Good. All right, so like I said, we're gonna split it up. So because number 25 is, we're not going to turn on the leftmost number, all right? And I should actually back up and say that when we converted from binary into decimal, we always started on the right-hand side and we counted up. Well, what we're going to do when we go in reverse from decimal to binary, we're always going to start on the left-hand side, all right? And we're going to count rightward down to the smaller number. And since we're not going to turn on this first zero here, and the reason being is because if we turn it on, then the value is 32, and 32 is greater than 25, so that's going to totally defeat the purpose. So we're always going to have the greatest number, even though, like I said, we have to put it there, we're always going to make sure that that greatest number is going to be a 0. All right, so we're always going to leave that one turned on. I'm sorry, turned off. So that means the very next number we're going to turn on, because we want to now add up whatever these numbers, whatever sequence we can, in order to make that number 25. So the very next digit, which is smaller than the target number, we're going to turn on. And so that will give us a total of 16. All right, and so if we take 25 and we subtract 16 from it, you know, that will then equal the value 9. So then that leaves us now with the rest of these digits here, 8421, to deal with. And so we need to look at these numbers and say, which numbers do I need to turn on in order to make the value 9? And as you can see, we have an 8 over here, and we have a 1 over here. So if I turn both of those on, that should give me the values that I need. Because if I flip on any of the other switches, I'm never going to be able to make that number 25. So what I'm going to do is I'm going to have to now take this one and flip that one onto a 1, and then take this one and flip that one onto a 1, while keeping these two here as a 0. So ultimately we would get a 0, 1, 1, 0, 0, 1. All right, and then that would be representative of the number 25. So let me do another example, and I'll show you again how it breaks down. But let me get to another screen here. Actually, you know what I could use right up top here. So let's just say, for example, you want to find the number 52. All right, so again, the first thing we're going to do is we're going to write the binary down. All right, and again, right above it, we're going to do the placeholders. That's a 1, that's a 2, that's a 4, that's an 8, that's a 16. So remember, we always want to go to the digit that's just above the target number. So if I do another 0, that's 32. 32 is not greater than 52, so I got to do one more, and that's 64. 64 is greater than 52, so I'm going to hold it there. All right, so now I got to figure out again, okay, what am I going to do? Well, we know that we cannot flip 64 into the on state into a 1 because that's going to be greater than 52, and that's going to kind of defeat the purpose of doing this. So this is going to remain a 0. But what I'm going to do is the very next digit I am going to turn on, all right? And so that would give me a value of 32. And so, whoops, flip back here. Where'd it go? There we go. So I'm going to flip. So what I'm going to do is I'm going to take the number 52, and I'm now going to subtract 32 from that, right? And that gives me a leftover of 20. So I look at the very next digit right over here, all right? And I determine, is that number greater than 20? It is not, all right? So that means I'm going to turn this on, all right? And then that would give me an additional 16. So I'm going to subtract 16 from the 20, and that would give me a balance of 4. And as you can see, well, I can't turn the 8 on. That's going to have to remain a 0 because that's greater than 4. Well, I need 4, so I'm going to turn the next digit on. All right, when I subtract those, that gives me 0 left, which means these last two must be 0. And so to calculate the number 52, to represent that in binary, we would have 0, 1, 1, 0, 1, 0, 0. All right, and then that's it. So that's basically how we use binary to add and or to convert, I should say, decimal into binary. And again, like I said, the importance behind that is because for us, we're familiar with number counting with the binary system. We're not familiar with, we're familiar with binary, we're familiar with number counting with the decimal system, not with the binary system. And so therefore, to understand, the difference between the two, that's basically how we can convert back and forth. And again, it's just the only importance behind understanding binary. It's our way to rationalize and to understand how a computer is thinking, because this is how the computer is talking amongst itself by using binary code, using a string of zeros and ones. And if we understand how computers think, we could then obviously, work with them and create the code that we need in order to make them function how we want them to. So again, outside the realm of computer science, we really won't be using this much, but at least you now have a better understanding of how we can kind of relate the binary system into the decimal system. All right, I'm going to stop there. We're going to go through one more unit, Unit 1.9, which will be next in a follow-up video. Have a great day, everybody.